this is forces 2 extended with momentum. Okay, momentum is the product of mass and velocity. This is a definition where you can just look at the formula and look at this term momentum has two properties to it, mass and velocity. I mean, another way you could look at momentum is the fact is how hard it is to stop something. It's not just how fast you're going that will decide how hard it is to stop something. Like if you had a bullet compared to a tennis ball. Usually when you throw a tennis ball at someone or at a wall, the tennis ball is reasonably easier to stop because its velocity is low. But if you had a bullet going to hit a wall, it's harder to stop because its velocity is high. So that means, yes, velocity does determine how hard it is to stop something. But the opposite can be true for mass. If you have a train and a car, and they're both crawling along at a walking pace, you could almost or possibly stop the car from rolling just with a human pushing it. Whereas the train, even if the train was going at a walking pace, no human could stand in front of it and stop it. So it depends on two things, mass and velocity. And if you look at the example down here, we have a train and a car. The car is going very fast, but a train going at 1 meter per second with the same momentum as a car going at 60 meters per second. So, and the momentum for each is just both of those multiplied together, so 60,000 Newton seconds. And in this case, if we try and stop each one, so let's say you could you drive them into some mud that has a uniform force applied to the car and train to stop it, they will both take the equal time to stop. So in other words, the train might have a large mass but very slow velocity, but it'll still take a long time to stop it because of that large mass. While a car has a lot smaller mass, but because it's going so fast, it will take a while to stop it. Impulse is another term, so there's two things. We've got momentum and impulse. So impulse is the force multiplied by time. So another thing that could be defined by a formula. Effectively, impulse, the size of your impulse is determined by the size of the force you push on something and for how long you're pushing it for. So if you push let's say we had a car, and you push that with a certain force over time, the longer you push that for, the greater your impulse. Or you could increase your force and push over just a short amount of time, and you might find that you get the same impulse. Okay, so impulse is just this force times time. Where is it important? It's important because impulse is equal to change in momentum. So if a 10 kg object is at rest, in other words it's got a momentum of 0, and it is then pushed with a force for a certain time, we can find the change in momentum by calculating the impulse. Because we've now found the change in momentum, we know the final momentum because we've gone from 0 when we're at rest to 200 Newton seconds. Once we've accelerated with a force, we can then find the speed just using the momentum equation, because we know the momentum we have when we got up to this speed is 200, so we can find our final speed, or velocity, sorry. Now, looking at collision, so this is the harder aspect of momentum, okay? For the first thing we can look at is an object going along at a certain velocity, hitting a wall and stopping, and having 0 velocity when it hits the wall. So for an object to stop, it must have no momentum after it's collided. And therefore the impulse needed to change to stop it is equal to the momentum before it stops, because it will be your momentum before minus your final momentum, which essentially is 0, and that gives you that means your momentum you had before will be a change of momentum. Ooh. So because impulse equals force times time, the collision can feel different. For example, a car, let's say beforehand it had a momentum of 100, so it could be a 100 kg car going at 1 meter per second. So if it had a momentum of that beforehand, that's an S, then when it hits the wall, it's going to lose all that 100 Newton seconds to 0, so that's its change of momentum, and that is fixed, okay, because it depended on what it was before, and in each example we're going to use it's the same. But how you crash is important. If we crash into a soft wall, then our change in momentum will be equal to force times time. This side stays the same, and if we then crash into something soft, it actually takes longer to stop, and that means the force will be lower because of that extra time. If we crash into something solid and hard, then the time will become small, and that means the force becomes large. Okay? So an example of that in a car might be that thing there. If you can see it, let's circle it in red. That thing there, an airbag. Or this thing here, the crumple zone. So those in your car are designed to make the crash longer, to increase the time, to reduce the force. So similar to an airbag, we could jump onto sand, or we could jump onto a trampoline. These increase your collision time, so the person will stretch the trampoline and stop down here. So the time has increased, and that means the force on the person to stop him is decreased. We'll look at conservation of momentum in a different video.